On December 24, 2024, inside the anxious mission control room at NASA, history fractured. An unyielding, lone robotic spacecraft plunged at 430,000 miles per hour, diving directly into the ultimate death zone of our local star system. As this vessel disappeared behind the raging, fiery solar halo, every single live telemetry screen went totally black, instantly plunging the entire dedicated team of brilliant engineers into a breathless, suffocating silence. Truly, humanity was witnessing the absolute craziest, most unfiltered chapter of celestial space exploration ever captured for a dramatic space documentary, boldly proving that our human species dares to cross any dangerous, unforgiving cosmic boundary. What they saw next would change everything we thought we knew. To fully grasp why the announcement that NASA just touched the Sun represents a historic milestone, we must examine the physical anatomy of our star. When humanity sent a spacecraft directly into this extreme cosmic environment, the goal was to reveal the staggering surprises hidden within its fiery architecture. To truly comprehend the exact data that NASA uncovered when they breached this boundary, we must establish three critical scientific definitions that govern this stellar atmosphere. First, we define the photosphere. The photosphere is the bright, glowing surface layer of the Sun, spanning a thickness of approximately 500 kilometers, where instruments record a baseline temperature of roughly 10,000 degrees Fahrenheit. This layer acts as the optical boundary of the star, from which visible light escapes into space. While classical astronomy viewed this as the definitive boundary of the star, NASA had to dive much deeper to unlock the ultimate surprise. Second, we define the corona. The corona is the outermost atmospheric envelope of the Sun, composed of highly ionized plasma that extends millions of miles into the vacuum of space. This outer atmosphere is dim compared to the bright solar disk, rendering it invisible to the naked human eye, only revealing its brilliant halo during a total solar eclipse. When NASA officially touched the Sun, they did not impact a solid surface. Rather, they flew directly into this vast, glowing crown of plasma. Third, we define the coronal heating problem. The coronal heating problem is an 80-year-old scientific paradox in modern astrophysics, describing the counterintuitive reality where the atmospheric corona reaches temperatures between 1 million and 3 million degrees Fahrenheit, making it hundreds of times hotter than the photosphere situated directly beneath it. This profound temperature inversion is the central surprise that has baffled the global scientific community for generations, serving as the primary scientific motivation for sending a mechanical scout directly into the Inferno to investigate. To understand how this grand surprise operates, science requires us to map the entire internal structure of the star, tracing the journey of energy from the inside out. The process begins at the absolute center, within the solar core. The core is an ultra-dense nuclear furnace extending outward to 25% of the solar radius, where immense gravitational forces trigger the continuous fusion of hydrogen atoms into helium. This reaction releases raw energy at a staggering temperature of 27 million degrees Fahrenheit. From the core, this immense energy enters the radiative zone, which extends out to 70% of the solar interior. Inside this incredibly dense layer, energy travels with extreme slowness, as light photons are continuously absorbed and re-emitted by tightly packed plasma particles, taking over 100,000 years to escape this atomic maze. Above this lies the convective zone, occupying the outer 30% of the interior, where energy transport shifts to physical boiling motion. Giant columns of hot plasma rise rapidly to the surface, cool down, and sink back down, a churning mechanism that creates the granular textures on the photosphere. Once energy passes the photosphere, it encounters the chromosphere, a turbulent layer roughly 2,000 kilometers thick, where temperatures briefly drop to a minimum of 7,000 degrees Fahrenheit. Immediately following this layer, the architecture of the star encounters a chaotic boundary called the transition region. Within this incredibly thin zone, the density of the solar plasma plunges by a factor of 10,000, while the temperature suddenly explodes exponentially from thousands of degrees to over 1 million degrees Fahrenheit, marking the official entrance into the corona. This bizarre thermal structure directly contradicts the second law of thermodynamics, a foundational rule of classical science which dictates that heat must naturally flow away from a hot source into cooler surroundings. According to basic physics, as you move further away from the central nuclear furnace of the core, the temperature should steadily drop. Instead, the outer atmosphere of our solar system presents a massive violation of this logic, proving that an invisible magnetic mechanism is actively pumping massive amounts of energy straight into the upper atmosphere while completely bypassing the surface. NASA just touched the sun to observe this exact phenomenon up close, confirming that the universe explained by modern science is full of dramatic, unexpected behavior. This spectacular stellar breakthrough demonstrates that our modern scientific community can successfully unveil deep, hidden cosmic secrets that defy every established textbook rule we have ever held about our dynamic surrounding environment within the cosmos. The profound surprise found within the solar corona is not an entirely new concept. Rather, this modern achievement rests upon a historical foundation of fierce intellectual rebellion. To appreciate the full weight of what humanity discovered when crossing this fiery threshold, we must first master two essential concepts that bridge the gap between abstract mathematics and cosmic reality. First, we define the solar wind. The solar wind is a continuous, outward-flowing stream of highly energized charged particles, consisting mainly of protons and electrons, that is constantly blasted from the solar corona into interplanetary space at supersonic speeds. This relentless stellar torrent floods the entire solar system, completely reshaping the local space environment of every single celestial body it directly encounters. Second, we define hydrodynamic equations. Hydrodynamic equations are a fundamental set of mathematical formulas used by physicists to describe and predict how fluids move and interact under the influence of physical forces. By treating the superheated, ionized plasma of the sun as a cosmic fluid, scientists can map its complex behavior across vast interstellar distances. To understand how these two concepts triggered a massive revolution in our shared understanding of the wider cosmos, any premium science documentary must transport its audience straight back to the rigid historical landscape of 1958. During this specific mid-20th century era, the firmly established consensus within the global realms of cosmology and astronomy held a remarkably peaceful, unchanging view of outer space. Mainstream researchers assumed that the vast gulfs separating planets were filled with a tranquil, empty vacuum. The sun was viewed merely as a distant, self-contained nuclear furnace that radiated light and illuminated the solar system without ever physically touching it. This quiet cosmic illusion was shattered when a brilliant, visionary young astrophysicist named Eugene Parker chose to look at our star through a radically different mathematical lens. Refusing to blindly accept the traditional static model, Parker applied the advanced hydrodynamic equations directly to the outer solar atmosphere. His intricate mathematical calculations quickly revealed a shocking, disruptive truth. The intense thermal energy trapped within the million-degree corona could not be structurally contained by the gravitational pull of the star. Instead, his equations mathematically demonstrated that the sun was essentially evaporating, continuously expanding outward in every direction, and generating a powerful, supersonic solar wind that flooded the surrounding interstellar void. When Parker submitted his revolutionary findings to a leading physics journal, the immediate response from the mainstream scientific establishment was swift and violently negative. The formal peer reviewers, who were highly respected academic experts of that era, flatly rejected his manuscript, openly ridiculing his elegant mathematical equations as utter nonsense. They aggressively claimed that his detailed work showed a complete, embarrassing ignorance of basic, elementary physics, confidently arguing that a supersonic stellar wind was an absolute physical impossibility. For several agonizing months, Parker faced severe professional isolation, harsh skepticism, and public mockery from his own peers. His groundbreaking paper remained buried and ignored until Subramanian Chandrasekhar, the eminent editor-in-chief of the astrophysical publication, who would later win the Nobel Prize in Physics, personally decided to intervene. While Chandrasekhar openly admitted that he was highly skeptical of the radical solar physics proposed, he meticulously verified Parker's hydrodynamic equations line by line and found absolutely no mathematical flaws. Recognizing the raw genius of the work, he boldly overrode the hostile, dogmatic reviewers and officially published the controversial paper in 1958. Just 2 years later, data transmitted from early space probes confirmed that the supersonic wind existed exactly as predicted, transforming an academic insult into one of the greatest, most celebrated human triumphs ever recorded. Decades later, NASA prepared to launch the ultimate space exploration mission directly into the solar atmosphere, executing an unprecedented act of institutional admiration. For the first time in agency history, a spacecraft was named after a living scientist, the Parker Solar Probe. In 2018, at the grand age of 91, Eugene Parker stood on the sunny Florida coast to witness the launch. With profound emotion in his eyes, he watched his mechanical namesake roar into space atop a giant column of brilliant fire. Though he passed away in 2022, his life's work was vindicated when the automated probe plunged deep into the stellar corona on December 24, 2024. The surprise NASA uncovered during that historic dive proved his early theoretical prophecy was flawless. But turning a theoretical paper into a physical shield capable of sailing this supersonic wind required an entirely new class of human engineering. Turning a theoretical prophecy into a physical mission required solving the ultimate engineering challenge: how a machine could survive inside the volatile atmosphere of a star without instantly vaporizing into a cloud of cosmic ash. This phase of space exploration represents a monumental chapter where theoretical science meets the unyielding limits of human manufacturing. To appreciate the data recovered during this plunge, we must dismantle the terrifying physics of the solar environment and examine the materials that protected the spacecraft. When looking at the extreme conditions of the solar corona, the immediate question that arises is how any physical structure could avoid melting. To answer this mystery, Science Explained provides a vital distinction between two concepts that are frequently confused in daily life: temperature versus heat. Temperature measures the speed of microscopic particles. On the other hand, heat measures the total thermal energy transferred to an object when those microscopic particles collide with its surface. Although the solar corona possesses an incredibly high temperature, reaching millions of degrees Fahrenheit, it is also a nearly perfect vacuum with an extremely sparse density. Because there are very few particles per cubic centimeter floating within this outer atmospheric envelope, the actual number of physical impacts against the spacecraft is incredibly low. Therefore, while each individual particle carries an immense amount of speed, the total heat load delivered to the ship remains manageable, allowing a well-designed shield to easily maintain structural integrity. However, managing a low heat load still requires an extraordinary defense against intense radiant energy. To survive the blinding environment, engineers created a thermal protection system measuring exactly 4.5 inches thick, relying heavily on a revolutionary substance known as carbon-carbon composite. This specific material consists of high-strength, reinforced carbon fibers embedded within a specialized woven carbon matrix, giving it the unique ability to endure mechanical stress and resist deformation even when exposed to thermal levels that would easily melt steel, titanium, or aluminum. The architecture of this 4.5-inch shield is an engineering masterpiece featuring a central core made of specialized carbon foam that is 97% air. This ultra-lightweight foam acts as an almost flawless thermal insulator, preventing the passage of energy. This porous core is sandwiched securely between two rigid panels of the carbon-carbon composite, creating a structure that is both remarkably light and incredibly tough. To maximize its defensive capabilities, the front surface of the shield is covered in a specialized white alumina ceramic paint, which reflects the vast majority of the blinding solar light back into space rather than absorbing it into the chassis. The performance of this thermal barrier creates a staggering physical contrast that highlights the sheer brilliance of modern engineering. While the outer, sun-facing side of the carbon shield absorbs a relentless barrage of radiation and glows at a white-hot temperature of 2,500 degrees Fahrenheit, the delicate interior of the spacecraft remains at an astonishing 85 degrees Fahrenheit, which is essentially comfortable room temperature. This massive thermal difference is maintained by a highly advanced active cooling system running through the body of the ship. This system utilizes purified, deionized water, which must be kept under immense high pressure to prevent it from boiling violently, continuously circulating the fluid through an intricate network of specialized titanium tubes. This pressurized water absorbs any stray heat that bypasses the primary shield and carries it away to radiator panels that radiate the energy into the cold void of space, ensuring computers never overheat. Protected behind this indestructible mechanical wall are the unburnable senses of humanity, a suite of 4 core scientific instruments designed to extract the deep secrets of our star and help us understand the energetic behaviors that influence distant galaxies across the vast universe. The first instrument is the Advanced Wide Field Imager for Solar Probe, WISPR, the only optical camera on board. WISPR captures unprecedented high-resolution images of the solar wind and coronal mass ejections from the inside out. Working alongside is FIELDS, an instrument designed to measure the electric and magnetic fields dancing through the plasma, allowing scientists to map the magnetic forces that shape space weather. The third instrument is SWEEP, which physically counts the most abundant particles within the solar wind, measuring their velocity, density, and temperature in real time. Finally, ISOIS acts as a high-energy particle detector, observing the accelerated electrons and ions that are whipped into a frenzy by solar flares. Surviving the sun's fury was one problem, but getting there forced scientists to confront a monumental logistical nightmare that completely defies our standard intuition about traveling through the void. To explore the deep cosmos, astrodynamics relies heavily on the concept of orbital velocity, the specific speed required for an object to maintain a stable path around a massive celestial body. When humanity targets the center of our neighborhood, this natural physics balancing act becomes an incredibly steep hill to climb. Most people assume that launching a mechanical probe toward a massive object with immense gravitational pull would be an effortless task, akin to throwing a rock down a deep well. In reality, modern space theory reveals that flying a spacecraft into the central star requires a far greater expenditure of raw kinetic energy than launching that identical vessel completely out of the entire solar system. This counterintuitive problem exists because of the inherited celestial momentum of our home planet. Earth travels around the Sun at a staggering lateral orbital velocity of approximately 67,000 miles per hour. According to the foundational laws of inertia, any object launched from the terrestrial surface automatically inherits this massive sideways speed. If a spacecraft simply fires its engines directly toward the Sun, that sideways velocity will cause it to overshoot the target entirely, trapped in an elongated loop. To descend toward the solar atmosphere, the vehicle must somehow cancel out nearly all of that 67,000 miles per hour of lateral momentum. Eliminating this vast kinetic energy requires a force so immense that no conventional chemical rocket could ever carry enough fuel to achieve it alone. To address this massive energetic deficit, NASA utilized one of the most powerful launch vehicles constructed, the mighty Delta IV Heavy rocket. This colossus of engineering was combined with a specialized star, 4874 third, upper stage, a powerful solid fuel booster designed to provide an explosive burst of speed. Together, these stages generated millions of pounds of thrust, ripping the small car-sized spacecraft away from the gravitational grip of Earth and throwing it into open space at a record-breaking speed. Yet, this escape was not enough to halt the sideways momentum inherited from our planet. The rocket pushed the probe into interplanetary space, but could not provide the immense deceleration necessary to drop the vehicle deep into the inner solar system. To solve this ultimate physics puzzle without carrying thousands of tons of impossible fuel, mission planners turned to a brilliant, elegant celestial mechanic known as a gravity assist. A gravity assist is a sophisticated orbital technique that purposefully uses the gravitational pull and orbital motion of a planet to alter the speed and trajectory of a spacecraft without consuming propellant. While traditional deep space missions use this planetary slingshot technique to accelerate outward, the Parker Solar Probe required the exact opposite application. Engineers had to use a planet as an interstellar braking system. The ideal cosmic partner chosen for this delicate orbital dance was Venus. Over a rigorous journey, the automated spacecraft executed 7 highly precise close flybys of our shrouded sister planet. The underlying mathematics of this trajectory are complex, yet terrifyingly unforgiving. Each time the probe soared past Venus, the planet pulled against the ship, bleeding off a portion of its lateral velocity. The energy stolen from the spacecraft was absorbed by Venus, slowing the probe and allowing the gravity of the Sun to pull the vehicle closer. This repetitive process altered the path of the spacecraft in a highly controlled manner. With each pass of Venus, the orbital loop of the probe was systematically crushed, shrinking its path and reshaping it into a tighter spiral. This orbital decay behaved exactly like a massive mechanical spring coiling tighter toward the central core of the star, or like slowly reeling in a tense fishing line. Each successive loop brought the probe to a new close approach, known as a perihelion, before allowing it to swing back outward toward Venus to prepare for the next gravity break. The precision required was absolute. An error during any flyby would send the spacecraft crashing into Venus or cause it to miss the solar corona entirely. Through this relentless series of planetary encounters, the laws of physics operating within our solar system were harnessed to achieve what once seemed completely impossible. Humanity watched as the momentum of Earth was stripped away by the silent fingers of gravity, proving that clever mathematical design can overcome environmental barriers in space. Once stripped of its excess terrestrial momentum, the craft finally plunged into the silent deep, where humans could no longer guide its steps. As the Parker Solar Probe descended past the point of no return on December 24, 2024, it crossed a boundary where human guidance became physically impossible. When a spacecraft plunges into the deepest valleys of a star's atmosphere, it enters a terrifying physical zone known as a radio blackout. A radio blackout is the phenomenon where radio wave signals are absorbed, disrupted, or blocked due to the high density of charged particles and electromagnetic radiation in a star's atmosphere. The superheated plasma, acting as a dense shield, chokes every transmission wavelength, leaving the ground control station on Earth blind and unable to track the ship for several days. The engineers at Mission Control could only sit before their frozen monitors, knowing that their creation was alone, racing at 430,000 miles per hour through a million-degree furnace. To survive this profound state of total blindness and existential isolation, the vehicle must rely entirely on its onboard autonomous guidance system. This technology is an automated computer network capable of making split-second control and correction decisions in real time, operating independent of human commands from Earth. Because radio signals take several minutes to travel between Earth and the inner solar system, and because the radiation completely severs that link anyway, waiting for human intervention would result in instant destruction. The computer on the probe must act as its own pilot, captain, and engineer, executing flaw-free decisions in a cosmic vacuum where a single mistake means immediate vaporization. The primary line of defense relies on solar limb sensors. These specialized optical detectors are mounted around the shadowed edge of the spacecraft, constantly staring into the blinding abyss to measure the exact position of the Sun. If the carbon composite thermal shield tilts by even a tiny fraction, the consequences are instantly catastrophic. A deviation that small would allow raw, focused sunlight to strike the unprotected flank of the spacecraft, melting its electronic instruments within seconds. To prevent this, the autonomous computer system must continuously read data from the solar limb sensors with absolute zero delay. The moment an anomaly is detected, the computer commands the heavy internal reaction wheels to spin rapidly, generating a precise gyroscopic force that rotates the giant shield back into its perfect defensive position directly facing the Sun. This entire corrective process occurs automatically, with a processing latency measured in mere milliseconds, happening far faster than a human being could ever perceive or react dynamically. While the autonomous computer brain protects the orientation of the ship, the physical body of the probe must endure a separate, brutal, mechanical battle against the laws of thermal expansion. At distances under 4 million miles from the solar surface, the structural materials face unimaginable physical stress. To prevent the spacecraft from tearing itself apart, engineers rejected traditional rigid aerospace construction and instead integrated a highly advanced network of flexible joints throughout the frame. These specialized flexible joints are mechanically engineered to allow the metal bones of the spacecraft to actively expand, flex, and bend in direct response to the extreme thermal forces instead of resisting rigidly. If the frame were completely stiff, the intense, uneven heat gradient would cause the structural metals to snap instantly under their molecular expansion. By allowing the machine to literally bend without breaking, the engineering marvel survives the violent currents of the cosmic furnace. This layer of supreme autonomy and mechanical adaptation offers a chilling glimpse into how a universe explained by modern astrophysics operates. In our ongoing quest to discover alien life across distant galaxies, or when theorists speculate about the grand infinite architectures of a theoretical multiverse, we often look outward for intelligence. Yet, this mission reminds us that the most isolated independent intelligence currently operating in the known cosmos is a human-made computer chip, executing cold, flawless logic while bathing in the atmosphere of a violent star. The ship flies as a lonely ghost, a solitary representative of our civilization enduring conditions that would dissolve any known biological organism completely. As the long days dragged on, the silence in the operations room grew heavier, emphasizing the terrifying reality of deep space exploration. The automated probe remained deeply submerged in the corona, a mechanical explorer operating entirely on cold, pure mathematics. The immense volume of scientific data downloaded to Earth in January 2025 marked a monumental turning point in modern astrophysics, permanently rewriting our understanding of stellar physics. For over 80 years, the scientific community was baffled by the mysterious mechanism heating the upper solar atmosphere, but the historic dive of the automated probe finally solved the infamous coronal heating problem. When researchers began analyzing the telemetry, they did not find a chaotic wilderness. Instead, they uncovered a beautifully organized, highly sophisticated masterpiece of fluid dynamics governed by natural laws. This breakthrough provides a window into the energetic operations that power our local star. Prior to this historic close approach, classical solar models assumed that the solar wind was ejected outward as a smooth, uniform spray of charged particles, radiating evenly in every direction. However, the Whisper camera captured a radically different reality from its unique position inside the outer atmosphere, shattering those simplistic assumptions. The high-resolution visual data revealed that the supersonic solar wind is actually born within highly complex, dynamic, and localized funnel-like structures that channel superheated plasma upward from the lower layers of the chromosphere. These giant magnetic funnels act as celestial nozzles, focusing the ionized material and accelerating it into violent, high-speed streams that twist through open space. This discovery provided concrete evidence that the solar atmosphere is an incredibly intricate, deeply textured environment where plasma dynamics are governed by local magnetic structures. As the spacecraft traveled deeper into these dense plasma funnels, its instruments detected an extraordinary phenomenon known as switchbacks, which represents a primary discovery within this atmospheric layer. Switchbacks are understood as the startling phenomenon where the magnetic field lines of the Sun bend and reverse their directional orientation by a full 180 degrees, twisting into an S-shape or zigzag pattern and traveling as violent, localized waves through the flowing plasma. These magnetic anomalies race outward through the atmosphere at extreme speeds, warping the surrounding space and creating massive fluctuations in the velocity of the solar wind. An advanced analysis rooted in quantum physics and stellar electrodynamics explains that as these zigzag magnetic structures move rapidly through the solar atmosphere, they do not behave like passive ripples. Rather, they operate like a massive cosmic whip, cracking violently into the surrounding space. This rapid whip-cracking motion injects immense turbulence into the ionized gas, forcing the charged particles into an extreme state of energetic excitement. As these tightly compressed magnetic kinks ripple outward, they continuously alter the local pressure gradients of the plasma, transforming the quiet vacuum into a roaring theater of kinetic action. The sheer mechanical power generated by these moving bends is completely unprecedented, demonstrating how simple geometric distortions in a magnetic field can violently accelerate matter to supersonic velocities. This continuous injection of kinetic energy ensures that the upper solar atmosphere remains in a permanent state of high-intensity agitation within the stellar core. This relentless whip-cracking motion directly triggers a catastrophic cosmic event known as magnetic reconnection, which provides the ultimate power source for the million-degree atmosphere. In the domain of plasma science, magnetic reconnection is understood as the violent process where opposite magnetic field lines within a highly conductive fluid are stretched to their absolute physical limits, snap suddenly, and rapidly link together into entirely new configurations, releasing an immense amount of stored magnetic energy instantly as extreme thermal energy and particle kinetic energy. When the zigzag bends of multiple switchbacks collide with one another inside the corona, their conflicting magnetic polarities are forced into immediate explosive contact. The resulting snaps act as microscopic atomic explosions scattered by the millions across the solar atmosphere, instantly accelerating local electrons and protons to near light speed, while releasing a blinding torrent of pure thermal power into the surrounding stellar vacuum environment. The enormous energy liberated by this continuous reconnection process is subsequently carried away by Alfvén waves, which function as the primary transport system of the solar atmosphere. By definition, Alfvén waves are specialized magneto-hydrodynamic waves that propagate directly along magnetic field lines within a conducting fluid like plasma, acting essentially as invisible cosmic conveyor belts that transport pure magnetic energy from deep within the stellar interior up into the high atmosphere. As these powerful waves surge along the guide rails of the Sun's magnetic network, they interact dynamically with the surrounding particles, directly converting their massive kinetic energy into microscopic thermal energy. This continuous wave dissipation acts like a giant microwave oven operating on a stellar scale, directly heating individual ions and electrons until their temperature skyrockets to millions of degrees Fahrenheit, providing the definitive answer to our cosmic questions regarding the thermal balance of this entire magnificent star system. Finally, the downloaded telemetry revealed an entirely separate plasma phenomenon known as the plasma U-turn, introducing an unprecedented layer of complexity to solar dynamics. During giant coronal mass ejections, which are massive explosions that lift billions of tons of magnetized gas into space, not all of the erupted material completely escapes into the outer solar system. Instead, the intense internal magnetic fields of the star act as a giant gravitational and electromagnetic anchor, forcing massive streams of superheated plasma to reverse direction and execute a literal U-turn back toward the solar surface. This returning matter falls downward along the field lines, crashing into the lower atmosphere and creating a highly complex energy feedback loop. This dynamic loop alters the structural stability of the corona, directly influencing the pathway and explosive power of the next solar eruption, a cyclical phenomenon never before included in our modern classical space models. The groundbreaking data revealing the Sun's dynamics is ultimately a profound story about the long-term survival of our entire modern human civilization. To understand why this matters, we must look at geomagnetic storms, which are defined as temporary disturbances of Earth's magnetosphere, occurring when the violent shock waves and magnetized clouds of the solar wind collide and interact dynamically with the protective magnetic shield of our planet. History warns us of this hidden environmental danger through the famous Carrington event of 1859, when a massive solar eruption triggered a super geomagnetic storm that fried the global telegraph network, causing telegraph equipment to burst into violent flames. If a similar memory of space history struck our highly interconnected modern digital world today, the consequences would be absolutely catastrophic. The sudden, massive electromagnetic surge would quickly destroy tens of thousands of active satellites in low Earth orbit, including the massive vital communication networks operated by progressive private aerospace corporations like SpaceX. It would instantly collapse critical global navigation systems, overload electrical power grids, and blow up high-voltage transformers across every single continent, plunging our vulnerable humanity into a dark global blackout lasting for many months. This existential threat is why we rely on space weather forecasting, which is the dedicated science of monitoring, analyzing, and predicting the changing environmental conditions on the Sun and in space that directly impact human technology and life on Earth. Until very recently, our planetary defense was severely limited, offering a mere 15 minutes of advanced warning before a major solar strike. The close-up data captured by the Parker Solar Probe changes everything, providing the foundational insights needed to completely revolutionize space weather forecasting. By witnessing the birth of the solar wind at its source, scientists can now extend early warning times from 15 minutes to several days. This crucial window gives utility companies and satellite operators ample time to safely power down systems, shielding trillions of dollars of infrastructure from destruction. Looking back, the journey of this small robotic spacecraft, carrying the name of a visionary scientist into the primordial fires of our star, brings a profound sense of closure. We human beings once viewed the sun as an unpredictable, terrifying deity, a chaotic furnace capable of extinguishing our modern world. Yet, the science explained by this historic mission reveals a deeper truth that feels almost like a glimpse into an ordered multiverse. Behind the violent, blazing facade of the corona lies a quiet, exquisitely beautiful mathematical harmony. Humanity did not just survive touching a violent star. We found that the cosmos operates on a structured, elegant blueprint. The universe isn't broken. Our map of it is just incomplete. What do you think? Does this change how you see our fragile place in the cosmos? I will keep exploring if there is more to uncover. Thank you so much for watching this video on our cosmic journey. Your support helps us explore the deepest secrets of the universe together. If you truly enjoyed discovering the wonders of the cosmos with us, please like, subscribe, and share your thoughts below. See you in the next episode.